Today, we're going to be talking about how to understand and explore the variation in possessive classifier systems in Oceanic. By that, we mean variation in inventory size of classifiers, variation of use, and variation in assignment between noun and classifier. We've got an overarching research question, which is, do these linguistic categorization systems have an impact on cognition? Just to introduce you to my co-authors, Grev and Ali, who will be on hand in the Q&A session later. And a big thank you to our consultants and stakeholders from across the world, especially to Anne-Laure Dott for helping running the experiments in New Caledonia. And thanks to Lisa Mack for her help on the PowerPoint today. And of course, a big thank you to the well over 100 participants from the 6 language communities in Vanuatu and New Caledonia. And fingers crossed we get to go back there soon. Today, we're going to be talking about, obviously, possessive classifier systems in Oceanic, and then our experimental approach and our novel way of approaching the analysis of the data using hierarchical cluster analysis. Now, in a language which has possessive classifier system, has a classifier system, each language has a different inventory size of possessive classifiers. Vatlongos, spoken in Vanuatu, has 4 classifiers, and the given noun can occur with different classifiers dependent upon the interaction between the possessor and possessed. This is called overlap. It's the ability of a noun to occur with different classifiers. So, for example, in Vatlongos, the noun for water occurs with the drink classifier in a context of drinking. The same noun can occur with a different classifier, here the general classifier, in a context of washing. North Ambrym, spoken in Vanuatu, has got 5 classifiers, so it differs to Vatlongos in the inventory size, but it also has a much more rigid assignment system than Vatlongos. Nouns typically only occur with 1 classifier, regardless of interaction. So in terms of assignment, North Ambrym functions more like a gender system. Here, the noun for water only ever occurs with the drink classifier, both in the context of drinking water, but also in the context of washing with water. And here, the general classifier would be ungrammatical in this sentence. So what's important to understand is that not all Oceanic classifier systems are the same, either in terms of classifier inventory size or in terms of noun classifier assignment. Okay, so let's move on to our experiments. We've designed a suite of experiments to investigate these possessive classifier systems in Oceanic, but rather than having just one experiment that targets all parts of our research question, we have several experiments which cover more than one aim. And this enables us to look at how participants use the classifiers and how this usage impacts cognition across a range of different contexts. Today, we're just going to be looking about the results of one experiment only, and that's the card sorting experiment. So let's look at our sample languages. We've chosen 6 different languages to look at in our project. Each one has a different inventory size of possessive classifiers. So we have Merei in Santo with 2 classifiers, Lewo and Iaai with 3, Vatlongos with 4 classifiers, North Ambrym with 5. And in New Caledonia, we have Nêlêmwa with 20 different classifier distinctions and Iaai with around 23. They not only differ in the inventory size of classifiers, they also vary in the semantic opacity or transparency of classifier membership. So from classifiers with simple semantics to ones with more complex semantics. And they also represent various stages of change from noun to classifier to gender, which is of interest for the typology of nominal classification and the origins of gender systems. Let's move on to our card sorting experiment. We made 60 different pictures, and the images represent the breadth of the membership of the classifiers in all of the languages in our sample. Participants had 3 tasks. First, to go through and name the pictures. This was to weed out any pictures that were inconsistently named. So in our analysis, we actually ended up with just 55 pictures to look at. The second task was a free sort. Participants sorted the pictures into groups or piles, into as many piles as they wanted. And it was up to them how they did it. They just had to base it on some perceived similarity. The third task was a structured sort that is based on the classifier inventory in their language. So participants had to group together items that use the same word denoting the classifier. Participants were also asked to name the piles that they had created as well, either by using the name of the classifier in the structured sort or a label or title in the free sort. The images also represent the different functional uses of entities, such as a pig, which is alive here, and one that's being roasted here. This allows us to see how participants group together similar entities across the different sorting tasks. The outcomes will help us explain whether the classifiers are cognitively salient, that is, do they structure cognition in general? Do the piles in the free sort match those in the structured sort, for example, or are the classifiers task dependent in cognition and only relevant in the domain of possession and don't cover up the world outside of possessive constructions? Okay, so let's move on to our analysis, hierarchical cluster analysis. Now, in hierarchical cluster analysis, the objects, or in our case, the pictures or nouns, are joined together hierarchically according to their similarity. A graphical tree representation called a dendrogram is produced, which you may be familiar with from historical linguistics, but this technique is not usually used widely in other areas of linguistics. Hierarchical cluster analysis represents the objects as leaves or branches on a tree, and in order to build the dendrogram, we need to calculate the distance between objects, and that's our basis for calculating similarity. So we create a distance matrix, and that's based on the Euclidean distance between objects, and then we merge the objects together based on their similarity or closeness in distance. Now, in reality, it's actually quite simple to do this using a statistical program such as R or SPSS. Let's just look at an example dendrogram which represents some toy data. Now, let's imagine a canonical gender system with fixed assignment. We've got 10 nouns in our system, nouns 1 to 10, and we have two classifications, classification 1 and 2, which may represent, for example, masculine or feminine gender, or the food or the drink classifier, for example. We also have 10 participants, and these 10 participants consistently assign nouns 1 to 5 to the first classification and nouns 6 to 10 to the second classification. The resulting dendrogram shows two clusters. Now, good clusters have two main properties. Firstly, objects within a cluster should be closely related. That is, that they should merge closer to the 0 distance mark. Objects within a cluster should be maximally distinct from other clusters. As we can see here, these two clusters merge together at the end of our scale, at the higher end of our scale. Now, the horizontal axis is obviously the most important axis. This is the level at which the clusters merge and show their similarity or closeness of the clusters. There's no vertical axis, and we can quite easily flip the nodes around if we want. This changes how things look visually, but doesn't actually affect the underlying interpretation. Now let's imagine a different system that for some nouns have a fixed or rigid assignment, but other nouns have speakers can vary in which classification is used for those nouns. So nouns 1 to 3 occur with classification 1, 8 to 10 solely with the classification 2, and nouns 4 to 7 are variably assigned to the two classifications. The resulting dendrogram shows these differences. There's still two main clusters, but these aren't as maximally distinct as in our previous system. They merge near the 6 distance mark. So it shows that there's a bit more similarity in this data set. Within these clusters, there are subclusters. The nouns merging at 0 are the nouns with a consistent pattern of assignment. So nouns with a fixed gender-like system, here and here, but also nouns with a consistent pattern of assignment, such as nouns 4 and 5, which were consistently assigned 7 and 3 respectively to the two different classifications. Now let's actually move on to our data, which is much more complex. So we've created dendrograms for each task and language, but we're just going to be focusing on just the dendrograms for the structured sort today. Even then, there's too many to show and discuss, so we're just going to look at a few different examples. We argue that hierarchical cluster analysis allows us to see patterns in the data, which gives a typology of classifier systems based on the variation of how participants sorted the pictures. Now here's our dendrogram for North Ambrym for the structured sort. To make things easier, we interpret the data. To make things easier to interpret, we present the dendrograms as part of a facet plot. So in the middle, we've got a list of nouns that represent the pictures, and on the left-hand side, we've got the dendrogram. Now that's the structuring of information of how participants group together the pictures. On the right-hand side is a stacked bar plot. And this shows the count data for which possessive classifier or method of classification, method of possession participant used for that picture. And that's been taken from the overall label given by the participant to the part or group which the picture was in. So the bar chart essentially maps onto the dendrogram information about which classifier the nouns occur with, and we can see if the clusters in the dendrogram match the classifiers used. So let's look, for example, at the first two nouns here, yam vine and yam. They both merged together at 0 in the dendrogram. They showing that the patterns of assignment was consistent, and we can see that all participants used the food classifier for those 2 items. Now, Ambrym has got 5 classifiers, but there are 3 main clusters, perhaps 4 in our data. One for the food classifier, which is represented green in the bar chart. One for drink, represented by the red in the bar chart, and one for general, represented by the purple here. And the 4th subcluster is for the fire classifier here. Now, there's a 5th classifier for basket entities. It's not used as often for classifying the pictures denoting baskets, and is actually a subcluster of the general classifier here. There are many objects that merge between the 0 and 1 point distance mark in our dendrogram. So it's showing that it's quite good clustering effects. We've got quite good distances between these clusters. They are quite distinct, these 3 main clusters. So what the dendrogram represents then is the actual use of the classifiers with the main clusters, with the main classifiers represented in the larger clusters, and the classifiers less used being subclusters of the main classifiers due to overlapping categories chosen by the participants. So on the whole, we're getting fairly fixed assignment for the major classifiers and more variable assignment for the minor classifiers. These are minor in the fact that they're used less and they have limited number of nouns able to occur with them. Let's have a look at the Vatlongos. The structure sort is much more complex. We're getting 3 clusters that roughly equate to 3 of the 4 classifiers, but these clusters aren't as distinct as the clusters we saw in Ambrym. They merge relatively higher up than they did in Ambrym, and within the clusters, the distances are much larger between the subclusters than we had in Ambrym. For example, there are no subclusters that merge between the 0 and 1 distance mark. Let's just look at some of these clusters here as well. So the cluster representing the food items, there's much more variation in how they were clustered together, how they're grouped together in the task. And the classifiers that we use also vary a lot between the food classifier, the general classifier, and the land classifier here in the light blue. We kind of expect this from a classifier system, as there should be more variation in assignment between noun and classifier. For the most part, the items that occur with the general classifier down here are more consistently assigned, but the items that occur with the food, land, or drink classifier are variably assigned. Compare this to the Ambrym data we just saw, where it was the minor classifiers that had the variable assignment. So it's not just a matter of strict or variable assignment when it comes to talking about these systems. There's structuring within the system itself, with some classifiers having nouns variably assigned and others having nouns more strictly assigned. Now let's look at Lewo. Lewo's got 3 classifiers: a food, a drink, and a general. In actual use, the classifier system functions fairly similar to Vatlongos in that speakers are fairly free in how nouns are assigned to classifiers. They can be variably assigned dependent upon semantics of use. But the dendrogram comes out very similar to Ambrym. There are lots of clusters that merge closer to 0, and there are 3 distinct clusters. The stacked bar plot representing the count data from the structured sort also looks more like Ambrym as well. The participants assign the pictures to different classifier piles more strictly. So let's put this into a table. And if we look at systems as a whole, Ambrym has a much more rigid or fixed assignment system than the other languages, especially in terms of the major classifiers. But it's variable in terms of the minor classifiers, such as the fire or basket, possibly due to reclassification of these items. Whereas Vatlongos and Merei, we haven't talked about Merei yet because we don't have enough time, but it patterns similarly to Vatlongos. We've got variable assignment in everyday use when we're using elicitation techniques, and also variable assignment of noun to classifier in the card sort. Now, Lewo has variable assignment in everyday use like Vatlongos, but much more rigid assignment in our sorting task. We believe that the task-dependent rigid assignment in Lewo is an intermediate stage between the more variable assignment found in the data in Vatlongos and the more rigid assignment found in Ambrym. Now, let's have a quick look at systems found in New Caledonia. We're just going to look at Iaai. It has a really large classifier inventory, and to see what patterns emerge here, especially with the minor classifiers. So the dendrogram shows good clustering effects here. There's lots of clusters merging closer to zero. We expect more variation in the clusters due to the large inventory size. The assignment of nouns to classifiers in the count data on the right-hand side suggests that the major classifiers, the general, the food, and the drink, may have a fairly rigid assignment. But the plant classifier here, which also has a large membership as well, similar to the land classifier in Vatlongos, is quite variable assignment here. The minor classifiers are also used less, and the nouns that occur with them show much more variation in assignment. For example, the catch classifier here, which is used for items of food that are caught, such as fish, or the sugarcane classifier, the ones shown in white here. They're much more used less, and the nouns that occur with them are variably assigned to other classifiers. So when we add this data in from the New Caledonian languages, we get a similar pattern for the major classifiers as we do for Lewo. These are variable systems every day, but speakers have an underlying classifier association based on semantics for the major classifiers, but with more overlap than in Lewo. There is also variable assignment of the nouns that can occur with the minor classifiers. We haven't looked at the Nêlêmwa data, but it patterns pretty similarly to the Iaai data. So in summary, what have we learned? Well, we can see a typology emerge from the data. There's a distinction in how speakers use the system every day and how speakers make judgments in the task. Increasingly, we're seeing structure in the system, so it's not as simple as describing a system as variable or rigid, but within the systems, we have to take into account the different type of classifier, major and minor, and even how the individual nouns behave. And that some classifiers are in competition with each other. For example, the land classifier in Vatlongos is competing for entities from the other large classifiers. That's similar to the plant classifier we saw in Iaai. And then again, we also have the minor classifiers, which also show variable assignment in their nouns. We argue that the classifier systems affect cognition in task-dependent ways. They're salient enough for speakers to use them for categorizing entities in a sorting task, and that within the task, we see a cognitive effect dependent upon classifier type. The major classifiers are more cognitively salient than the minor ones, as they're used more often and attract more nouns than the minor classifiers. So in summary, we found that hierarchical cluster analysis is a very useful method for finding patterns in the data and interpreting categorization across languages. A fine-grained typology emerges from the different types of data, so how the objects merge together in different classified clusters, but also by looking at the count data from the names of the piles or the groups made in the structured sort. Finally, Oceanic possessive classifiers can't simply be described as being fixed or variable in their assignment systems, because when you open them up and look inside, each classifier is doing something different, and some have more cognitive pull than others do. In our next stage of analysis, we want to cross-reference our different experiments that we've conducted so far and our future experiments. We've got some good data so far from a free listing experiment, which is going to help us analyze the different membership size and openness of the classifiers, and should give us a better definition of classifier type between our major and minor classifiers. We want to investigate the cognitive impacts of the classifier systems on general cognition, and we can do this by comparing the structured classifier sort versus the free unconstrained sort results. We look forward to returning to the field with our experiments. Thank you very much, and looking forward to questions and comments next.